When you step outside on a quiet night and look up, far away from the city lights, the sky begins to reveal its secrets. If the night is dark enough, you will notice something different from the ordinary stars you usually see. Stretching across the sky like a faint glowing path, there is a hazy band of light. It looks soft, almost like a mist, but it is not a cloud. That faint band is the Milky Way. It is our galaxy, our cosmic home, the vast system of stars, gas, and invisible matter that we live inside. The reason it looks like a cloudy streak instead of sharp points of light is simple. There are just too many stars packed together. Your eyes cannot separate them one by one. Imagine standing in the middle of a city and looking at all the lights in the distance. When there are only a few lights, you can count them. But when there are millions close together, they blur into a glow. That is exactly what happens when we see the Milky Way. We are looking into the crowded disk of our galaxy, and the light of billions of distant suns merges together. The Milky Way is enormous. Astronomers estimate it is about 100,000 to 120,000 light years across. A light year is the distance that light travels in 1 year. Light moves incredibly fast, 300,000 kilometers every second. In 1 second, it could circle Earth more than 7 times. In 1 year, it travels about 9.5 trillion kilometers. So if you could ride a beam of light going as fast as anything possibly can, it would still take you 100,000 years to cross the Milky Way from one side to the other. Numbers that large are hard to picture, but that is the scale of our home. Inside the Milky Way, there are between 100 billion and 400 billion stars. The reason we cannot give an exact number is because many of these stars are small, faint, and hidden behind clouds of dust. Most of them are not big like our sun, but are cooler, dimmer red dwarfs. Even though they are faint, they are extremely common. Alongside stars, the Milky Way also contains vast amounts of gas and dust. These are the raw materials for building new stars and planets. And beyond that, most of the galaxy's mass is something we cannot even see: dark matter. Dark matter does not give off light, but its gravity shapes the galaxy, holding it together and controlling how stars move. Without dark matter, the galaxy would fly apart. The Milky Way has a structure. It is not just a random ball of stars. It is a spiral galaxy, which means it has arms that wind outward, like the swirls in a pinwheel. These spiral arms are places where stars are born. Giant clouds of hydrogen gas collapse under gravity, forming hot young stars that shine brightly and light up the clouds around them. Our solar system is not in the center of the galaxy, nor in one of the biggest arms. Instead, we sit in a smaller branch, called the Orion Arm or Orion Spur, about 27,000 light-years from the middle. That puts us roughly halfway between the galactic center and the edge. We live in a quiet neighborhood of the galaxy, far away from the crowded, violent core. At the center of the Milky Way is the galactic bulge, a thick, dense region filled with stars, many of them old and reddish. Hidden inside this bulge is one of the most mysterious objects in the universe, Sagittarius A star, the supermassive black hole at the very heart of the galaxy. It has the mass of about 4 million suns. We cannot see it directly because no light can escape a black hole, but astronomers know it is there because of the way stars near the center race around at incredible speeds. They are like leaves caught in a whirlpool, orbiting something invisible but immensely heavy. This black hole is the anchor of our galaxy, the monster that holds everything in place. But from Earth, we do not see it directly. We only see the glow of the stars around it. Beyond the disk and bulge lies the galactic halo. The halo is a faint, extended sphere surrounding the galaxy, made up of scattered stars and globular clusters. Globular clusters are huge, ancient groups of stars, sometimes hundreds of thousands packed tightly together. These stars are some of the oldest in the universe, more than 12 billion years old. The halo also contains much of the dark matter that gives the Milky Way its mass. Our solar system is always moving. The Sun, along with all the planets, orbits the center of the Milky Way at a speed of about 828,000 kilometers per hour. Even at that speed, It takes about 225 to 250 million years to make a full orbit. This means that since the Earth formed 4.5 billion years ago, we have completed only about 20 orbits around the galaxy. In other words, during the entire time that dinosaurs lived and became extinct, the solar system did not even make one complete lap. Human history is so short compared to these timescales that from the galaxy's perspective, we have barely begun our journey. When we see the Milky Way in the sky, we are looking into the past. Light does not travel instantly. It takes time to move across space. The nearest star after the Sun is Proxima Centauri, about 4.2 light-years away. This means the light we see from it tonight left that star more than 4 years ago. Some stars we see are thousands of light-years away, so their light began its journey before humans had even built the first cities. In the Milky Way, there are stars tens of thousands of light-years away, so the light reaching us now began its journey when humans were still hunter-gatherers. Looking at the Milky Way is like opening a history book written in light. The galaxy itself is ancient. It began forming more than 13 billion years ago, not long after the Big Bang. In its earliest days, small clumps of stars and gas merged together to form larger structures. Over time, these merged into the Milky Way. The first stars that formed were massive and burned quickly, ending their lives in supernova explosions. These explosions created heavier elements which later generations of stars incorporated. Our Sun, which formed 4.6 billion years ago, is part of this later generation. The iron in our blood and the calcium in our bones were forged in ancient stars that died long before Earth existed. In this way, the Milky Way is not just our home, but the source of everything that makes us possible. The Milky Way is always changing. Stars are born in nebulae, live for millions or billions of years, and then die as white dwarfs, neutron stars, or black holes. Supernova explosions scatter heavy elements into space, enriching the galaxy and allowing new planets and life to form. The spiral arms are maintained by waves of density that move through the disk, compressing gas and triggering star formation. The Milky Way also interacts with smaller galaxies. Some of these dwarf galaxies are being pulled apart and absorbed. Streams of stars left behind by these interactions can be traced across the sky. In billions of years, the Milky Way will collide with the Andromeda galaxy, and the two will merge to form a new, larger galaxy. For humans, though, the Milky Way is not just a scientific object. It is also a source of inspiration and mystery. Ancient cultures around the world created myths about the glowing band in the sky. Some thought it was a river, others a road for spirits, others the spilled milk of a goddess. Even without telescopes, people recognized that it was something beyond ordinary. Today we understand it in scientific terms, but the sense of awe remains. Knowing that the faint glow is the light of billions of distant suns makes it even more powerful. Modern astronomy allows us to study the Milky Way in many ways. Optical telescopes show us the stars, but interstellar dust blocks much of the light from the central regions. Radio telescopes can see through the dust, revealing the spiral structure. Infrared telescopes can also penetrate dust clouds, showing stars that would otherwise be hidden. X-ray and gamma-ray telescopes detect the most energetic events, such as supernova remnants and activity around black holes. By combining all these observations, astronomers can build a complete picture of the Milky Way. When we talk about stars in the Milky Way, astronomers classify them into populations. Population I stars, like the Sun, are relatively young and contain more heavy elements. They are found mostly in the disk and spiral arms. Population I stars are older, with fewer heavy elements, and are found in the bulge and halo. The very first stars, which astronomers call population 3, no longer exist, but they would have been massive, short-lived, and composed almost entirely of hydrogen and helium. By studying the metallicity, or the abundance of heavier elements in stars, scientists can trace the history of the galaxy's chemical enrichment. To measure distances in the galaxy, astronomers use several methods. For nearby stars, they use parallax, the apparent shift in position of a star when observed from different points in Earth's orbit around the Sun. For more distant stars, they use standard candles, such as separated variable stars, whose brightness varies in a predictable way. By knowing how bright a star truly is, and comparing it to how bright it appears, astronomers can calculate its distance. These methods allow us to map the structure of the Milky Way, even though we are inside it and cannot see it from the outside. From Earth, the Milky Way is best seen in areas with little light pollution. In the northern hemisphere, the bright center of the galaxy is visible in the summer toward the constellations Sagittarius and Scorpius. In the southern hemisphere, the view is even more spectacular, with a central bulge high overhead. In both hemispheres, the Milky Way connects us directly to the larger cosmos. It reminds us that our solar system is part of something far bigger, something that extends far beyond what we can ever travel. When we leave behind the comfort of our solar neighborhood and begin traveling deeper into the Milky Way, the first great structures we encounter are the spiral arms. These arms are not physical arms in the sense of rigid structures, but rather long, sweeping regions of stars, gas, and dust that wind outward from the galactic center like the curved blades of a pinwheel. From above, the Milky Way would appear as a glowing disk with several of these spiral arms curling outward. Since we live inside the disk, we cannot see this structure directly, but astronomers have mapped it using careful observations of stars, star clusters, and radio signals from gas clouds. The spiral arms are where much of the visible activity of the galaxy happens. They are sites of constant creation. Enormous clouds of hydrogen gas, stretching for hundreds of light years, collapse under their own gravity and form new stars. The spiral arms, therefore, are like stellar nurseries, places where the galaxy continually renews itself. These regions are marked by glowing nebulae, star clusters, and massive young stars that shine brightly and illuminate the gas around them. Our solar system lies in a smaller arm called the Orion arm, or Orion's spur, located between two of the larger arms, the Sagittarius arm and the Perseus arm. The Orion arm is only about 3,500 light-years across and 10,000 light-years long. Even though it is smaller, it contains many familiar objects, including the Orion Nebula, the Pleiades star cluster, and the bright stars that form the constellations of Orion and Taurus. When we look into the night sky and see these famous patterns, we are actually looking at part of our own spiral arm. The larger arms of the galaxy, such as the Sagittarius and Perseus arms, are much grander. They are full of bright nebulae and clusters that mark active regions of star formation. One of the most famous is the Eagle Nebula, where dense columns of gas, sometimes called the pillars of creation, are giving birth to new stars. Another is the Carina Nebula, a vast region of gas and dust lit up by massive young stars. These regions show us that the galaxy is not static, it is alive with constant cycles of birth and change. The way spiral arms form is fascinating. They are not made of fixed collections of stars. Instead, they are patterns created by what astronomers call density waves. Imagine cars on a highway. The cars move at different speeds, but sometimes traffic slows down in one area and cars bunch together. The jam slowly moves along the road, but the cars themselves eventually pass through it. Spiral arms work in a similar way. They are regions where the density of stars and gas is higher. As material moves through these regions, gas clouds are compressed, triggering star formation. Massive, bright stars light up these regions, making the spiral arms visible. Eventually, those massive stars burn out and die, but by then new stars have formed elsewhere in the arm, keeping the pattern alive. Within the spiral arms, stars form in groups rather than alone. These groups are called star clusters. There are two main types, open clusters and globular clusters. Open clusters are loose associations of a few hundred to a few thousand stars, all born from the same cloud of gas. They are relatively young, often just a few million to a few 100 million years old. An example is the Pleiades, also known as the Seven Sisters, which can be seen in the night sky with the naked eye. Open clusters gradually break apart as their stars drift away, joining the general population of the galaxy. Globular clusters, on the other hand, are very different. They contain hundreds of thousands of stars, packed tightly together in spherical shapes. Most globular clusters are much older, often more than 10 billion years old, and they are found not in the disk but in the galactic halo. In this chapter, our focus is on open clusters, since they are products of the spiral arms. They show us how the arms act as cradles for new generations of stars. The life of a star begins when a cloud of gas and dust collapses under gravity. As the cloud contracts, it heats up. Eventually, the core becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse to form helium, releasing energy in the process. This energy pushes outward, balancing the inward pull of gravity, and a new star is born. If the star is massive, it burns brightly and lives a short life, perhaps only a few million years. If it is smaller, like our Sun, it shines steadily for billions of years. The spiral arms are also home to some of the most spectacular objects we can see, nebulae. There are different types of nebulae. The Mission nebulae, like the Orion Nebula, glow because they are energized by the radiation from nearby young stars. Reflection nebulae shine by reflecting the light of stars. Dark nebulae are thick clouds of dust that block the light behind them, appearing as dark shapes against the brighter background of the Milky Way. Each nebula tells part of the story of star formation, showing the raw material from which stars and planets are built. Massive stars formed in the spiral arms do not live long. They burn through their fuel quickly and end their lives in violent supernova explosions. These explosions are not only dramatic but also essential. They scatter heavy elements into space, elements like carbon, oxygen, and iron, which are necessary for planets and life. Without supernovae, the galaxy would not have the chemical richness needed for worlds like Earth. The spiral arms, therefore, are not just nurseries for stars, but also factories that enrich the galaxy, making life possible. The spiral arms are also important for another reason. They guide the structure of the galaxy. The density waves that create the arms influence how gas and stars are distributed. They shape the flow of material and control where new generations of stars will appear. This means that the spiral arms are not just beautiful, they are fundamental to the ongoing life of the galaxy. When we observe the spiral arms from Earth, we cannot see the entire structure at once because we are inside it. Instead, we see sections of the arms marked by bright regions of star formation. Astronomers use radio telescopes to map hydrogen gas throughout the galaxy, which helps reveal the spiral pattern. They also use observations of certain types of stars like Cepheid variables to measure distances and place stars within the arms. Over decades of work, they have built a model of the Milky Way's spiral structure, showing that it has 4 major arms and several smaller spurs, including the one we live in. Traveling through the spiral arms in our imagination allows us to appreciate the scale of these structures. Each arm stretches for tens of thousands of light years. Within them are countless stars at every stage of life, from newborns just forming to ancient ones nearing their end. The arms are busy, active regions, full of gas, dust, light, and energy. They are the places where the galaxy is most alive. If you look at photographs of other spiral galaxies, such as the Whirlpool Galaxy or the Andromeda Galaxy, you can see their arms clearly. These images give us an idea of what our own Milky Way would look like from outside. Glowing blue regions mark areas of young, massive stars. Dark lanes of dust cut through the arms, hiding some of the light. The spiral structure is both orderly and dynamic, a balance of patterns and constant change. Our Milky Way is one among many, but it shares this same grand design. The spiral arms remind us of cycles. Stars are born, live, and die, enriching the galaxy with their material, which then forms new stars and planets. The arms are the visible signs of these cycles, the regions where the process is most concentrated. When we say the Milky Way is alive, we mean that it is not static. It is always in motion, always changing, always renewing itself. For us, the spiral arms also carry a sense of connection. The Sun, although it formed billions of years ago, was once part of such a star-forming region. The atoms in our bodies, carbon, oxygen, nitrogen, were created in stars that lived and died in earlier arms. In a sense, we are products of these cycles. The spiral arms are not distant curiosities. They are part of our own story. As we move through the spiral arms in this chapter, the main lesson is creation. The arms are the places where the galaxy builds its future, where new light is born. They are vast, elegant structures shaped by gravity, waves, and time, and they are filled with the beauty of nebulae and clusters. To look into the spiral arms is to see the engines of the galaxy at work. As we travel farther inward toward the center of the Milky Way, the scenery around us begins to change. The spiral arms we left behind are lively and colorful, full of glowing nebulae and newborn stars. But here, in the regions closer to the galactic bulge and in the surrounding halo, we encounter something very different: the galaxy's old stars, the survivors from its earliest days. These stars are like guardians of memory, carrying with them the history of how the Milky Way was formed and how it has changed over billions of years. One of the most striking features of these regions is the presence of globular clusters. Globular clusters are enormous, spherical groups of stars bound tightly together by gravity. Each cluster can contain hundreds of thousands, or even millions of stars. Unlike the open clusters we saw in the spiral arms, which are young and loosely arranged, globular clusters are ancient and compact. Most of them are more than 10 billion years old, meaning they formed not long after the galaxy itself began to take shape. From Earth, globular clusters appear as faint, fuzzy spots in the night sky. Through a telescope, they reveal themselves as breathtaking swarms of stars, densely packed, shining like glittering jewels. The Hercules cluster, for example, is about 25,000 light-years away and contains hundreds of thousands of stars. Another, Omega Centauri, is so massive that it may once have been the core of a smaller galaxy absorbed by the Milky Way. These clusters orbit the galaxy in the halo, moving far above and below the disk, and their ancient stars give us a window into the early universe. What makes globular clusters so important is their age. Because they are so old, their stars are composed mostly of hydrogen and helium, with very few heavier elements. Astronomers call these low metallicity stars. By studying them, we learn about what the universe was like before many generations of stars had lived and died. These clusters are fossils of the Milky Way's earliest history, carrying information about the time when galaxies were first forming. As we look more closely at individual stars in these regions, we notice that many of them are red giants. A red giant is a star that has used up the hydrogen fuel in its core. When hydrogen runs low, the core contracts and heats up, while the outer layers expand. The star becomes enormous, often hundreds of times larger than the Sun, and its surface cools, giving it a reddish color. Red giants shine brightly and can be seen from great distances. They represent a late stage in a star's life, a reminder that even stars must age. Eventually, a red giant sheds its outer layers, creating a planetary nebula. What remains behind is a white dwarf, a dense, Earth-sized remnant of the star's core. White dwarfs no longer generate energy through fusion. They simply cool and fade slowly over billions of years. The regions we are now passing through are filled with such remnants, stars that once shone brightly but are now quiet, cooling embers. Some may already be so faint that they are nearly invisible. Together, red giants and white dwarfs tell the story of stellar aging. They show us what will one day happen to our own sun, which will expand into a red giant in about 5 billion years and eventually become a white dwarf. The older regions of the Milky Way are reminders of the galaxy's past and hints of its future. Another fascinating aspect of these ancient regions is the presence of population 2 stars. Astronomers classify stars into different populations based on their age and chemical makeup. Population stars, like the Sun, are relatively young and rich in heavier elements. They are found mostly in the spiral arms. Population stars, by contrast, are older with very few heavy elements. They are found in the bulge and halo, including the globular clusters we have been describing. The very first stars, called population 3, no longer exist, but studying population stars gives us clues about them. These old stars are like records of the early galaxy, preserving conditions from billions of years ago. The bulge of the Milky Way is also different in character from the spiral arms. Instead of being filled with bright blue young stars and nebulae, the bulge is dominated by older, redder stars. It is crowded and dense, with stars orbiting in more random directions rather than the orderly rotation we see in the disk. The bulge extends thousands of light-years in each direction from the center and contains a significant fraction of the galaxy's total stellar mass. It is here that we begin to feel the gravitational pull of the core more strongly. Astronomers study the bulge and the halo to understand how the Milky Way grew. Evidence suggests that our galaxy formed through the merging of smaller protogalaxies in its early days. Some of the stars we see here may not have been born in the Milky Way at all, but in dwarf galaxies that were later pulled in and absorbed. Streams of stars in the halo, which are remnants of these mergers, confirm that the Milky Way is still growing by capturing smaller neighbors. The motions of stars in the bulge also provide important information. Unlike stars in the disk, which follow nearly circular orbits around the center, stars in the bulge move in more chaotic paths. This is partly because the bulge is influenced by a bar-shaped structure of stars that stretches across the central region. The Milky Way is classified as a barred spiral galaxy because of this feature. The bar funnels gas inward, feeding star formation in the bulge and fueling the supermassive black hole at the very center. When we think about the old stars of the bulge and halo, it is worth remembering their role in the chemical evolution of the galaxy. Early stars contained almost no heavy elements, but as they lived and died, they produced elements like carbon, oxygen, and iron in their cores. When they exploded as supernovae, these elements were scattered into space, enriching the gas that would form later stars. Each new generation of stars contained more heavy elements than the one before. Our own sun is part of this later generation, enriched enough to form planets and life without the long history of earlier stars. Earth and everything on it could not exist. The ancient regions of the Milky Way also remind us of time on a cosmic scale. While human history spans only a few thousand years, these stars have been shining for billions. Some globular clusters are older than Earth itself. They have survived the entire history of our planet, orbiting silently in the galaxy's halo while continents drifted, species evolved, and civilizations rose and fell. Looking at them is like looking at eternity. From a practical point of view, studying these old stars helps astronomers measure the age of the galaxy. By determining the ages of globular clusters, scientists can place a lower limit on how old the Milky Way must be. The oldest clusters are more than 13 billion years old, meaning our galaxy began forming not long after the universe itself. These ancient structures are the closest we can come to direct evidence of the galaxy's beginnings. So as we travel through the inner regions of the Milky Way, what we see is not youth and creation as in the spiral arms, but age and memory. The globular clusters, the red giants, the white dwarfs, and the low metallicity population 2 stars all tell the story of a galaxy that has been alive for billions of years. They are the old guardians of the Milky Way, witnesses to its entire history. The farther we move into the Milky Way, the busier the galaxy becomes. While the spiral arms stretch widely, with stars spaced out and great clouds of gas forming new suns, the inner regions are much denser. Here in the crowded heart of the galaxy, the environment is unlike anything we are familiar with in our quiet solar neighborhood. Near the Sun, the closest star to us is Proxima Centauri, about 4.2 light-years away. That means if you traveled at the speed of light, it would still take you over 4 years to reach it. On average, stars in our region are several light-years apart, which gives each one plenty of space. But near the galactic center, this is not the case. There, stars can be packed as closely as 0.1 light-years apart, sometimes even closer. Imagine the night sky from a planet orbiting one of those stars. Instead of a few thousand stars visible, as we see on Earth, you would see millions blazing across the sky so brightly that the night might never truly be dark. This density of stars creates a unique environment. In our part of the galaxy, stars rarely interact directly with each other. In the core, however, close encounters are more common. Stars tug on each other with their gravity, altering orbits and sometimes even colliding. Collisions are extremely rare on human timescales, but over billions of years in such a crowded place, they happen often enough to create unusual types of stars. For example, when 2 stars merge, they can form what is called a blue straggler. These stars look younger and hotter than they should be, because the merger gives them new fuel to burn. The core is also home to many binary and multiple star systems where two or more stars orbit each other closely. Some of these pairs are stable, but others interact dramatically. In certain systems, one star may be a normal star while the other is a dense remnant like a neutron star or a black hole. As gas from the normal star falls onto its compact companion, it heats up and produces intense X-rays. These systems are known as X-ray binaries, and they are common in the crowded regions near the galactic center. The radiation environment here is extreme. The presence of so many massive stars means that ultraviolet radiation floods the region. Stellar winds, streams of charged particles flowing outward from stars collide and stir up the interstellar medium. When these massive stars reach the end of their short lives, they explode as supernovae, sending shockwaves through the region and releasing even more energy. The central parts of the Milky Way are therefore filled with high-energy processes that we cannot see with our eyes, but that telescopes detect at X-ray and gamma-ray wavelengths. Dust also plays a significant role in shaping what we can see from Earth. The galactic core lies in the direction of the constellation Sagittarius, but when you look toward it in visible light, most of the stars are hidden by thick dust clouds. This is why the Milky Way appears as a mottled band with dark lanes running through it. Those dark regions are not empty space, but dense curtains of dust that block light. To overcome this, astronomers use infrared telescopes, which can see through the dust, and radio telescopes, which detect signals from gas. By combining data from different parts of the electromagnetic spectrum, scientists can build a detailed map of the core, even though it is invisible to ordinary sight. One of the most fascinating discoveries about the galactic core is the group of stars called the S stars. These stars orbit extremely close to Sagittarius A, star the supermassive black hole at the center. Some complete their orbits in just a few years, moving at speeds of thousands of kilometers per second. By tracking these orbits carefully, astronomers were able to confirm the presence of a massive, invisible object exerting a powerful gravitational pull. This was one of the strongest pieces of evidence for the existence of Sagittarius A star, which we will explore in the next chapter. The S stars also allow scientists to test theories of gravity in extreme conditions. Their orbits match the predictions of Einstein's theory of general relativity, providing yet another confirmation of this fundamental law of physics. The galactic core also contains what astronomers call the central molecular zone. This is a massive region filled with giant molecular clouds, dense concentrations of gas that stretch for hundreds of light years. Some of these clouds contain enough material to form millions of stars. Conditions here are turbulent, with gas moving at high speeds, compressed by shock waves, and stirred by gravitational forces. Star formation in this zone is intense, but often hidden behind thick dust. When new stars are born here, they are often massive and hot, adding even more energy to the environment. Another feature of the core is the abundance of pulsars. Pulsars are rapidly rotating neutron stars, the remnants of massive stars that exploded as supernovae. As they spin, they emit beams of radio waves or other radiation like cosmic lighthouses. From Earth, we detect these beams as regular pulses, sometimes hundreds of times per second. Pulsars are valuable tools for astronomers because their timing is so precise. In the crowded galactic core, pulsars can help map the distribution of matter and test gravitational theories. The bulge that surrounds the core is also worth examining. It is made up mostly of old stars, similar to those we saw in globular clusters, but arranged in a dense spheroidal shape. Unlike the disk, where stars move in fairly ordered orbits, the stars in the bulge move in more random paths. This creates a different dynamic, with stars swirling around in all directions. The bulge is also thought to contain a bar-like structure, a long stream of stars that stretches across the core. This bar plays an important role in funneling gas inward, where it can fuel both star formation and the growth of the central black hole. Studying the crowded heart of the galaxy is not easy. Because of the dust and the distance, about 27,000 light-years from Earth, astronomers must use advanced techniques and instruments. The European Southern Observatory's Very Large Telescope in Chile and the Keck Observatory in Hawaii have both tracked the motions of stars near Sagittarius A. Star with extraordinary precision. The Hubble Space Telescope and newer instruments like the James Webb Space Telescope provide infrared views that cut through the dust. Radio telescopes, such as those in the Very Large Array, detect signals from gas clouds and pulsars. By combining all this information, scientists build a three-dimensional picture of the galactic core, revealing its complexity layer by layer. The crowded core is also important because it shapes the evolution of the entire galaxy. The stars, gas, and black hole at the center influence the orbits of stars farther out, the flow of material in the spiral arms, and even the rate of star formation across the disk. The Milky Way is not just a collection of stars moving independently, it is a connected system, with the core playing a central role in its stability and growth. For us, imagining the crowded galactic core helps us appreciate how different conditions can be in other parts of the galaxy. Our solar system is located in a relatively calm, quiet region where stars are far apart and life had the chance to develop without constant disruption. If Earth had been located in the galactic core, it is unlikely that life as we know it could have survived. The radiation, supernovae, and close stellar encounters would have created an environment far too unstable for billions of years of biological evolution. In this sense, our location is fortunate. We are close enough to study the core, but far enough to be safe from its dangers. At the very heart of the Milky Way lies Sagittarius A star, a supermassive black hole that has fascinated astronomers for decades. To understand why this object is so important, we need to begin with the basic idea of what a black hole is. A black hole is not an object in the ordinary sense. It is a region of space where gravity is so strong that nothing can escape, not even light. Gravity comes from mass, and the more mass something has packed into a small space, the stronger its pull. When enough matter is squeezed into a small enough volume, the escape speed, the speed needed to break free, exceeds the speed of light. At that point, nothing can get out. That boundary is called the event horizon, and inside it lies the black hole. Black holes come in different sizes. The smallest ones are stellar black holes, created when massive stars collapse at the end of their lives. These may have a few times the mass of the Sun. At the other extreme are supermassive black holes, which contain millions or billions of times the Sun's mass. Every large galaxy we know of seems to have one at its center. Sagittarius A star is our galaxy's central black hole, with about 4 million times the mass of the Sun. What makes Sagittarius A star extraordinary is not only its mass but also its location. It sits in the very middle of the Milky Way, about 27,000 light-years from Earth. Our entire galaxy, hundreds of billions of stars, clouds of gas and dust and dark matter, rotates around this center. Sagittarius A star is not the only thing keeping the galaxy together. Dark matter plays the largest role, but its presence marks the focal point around which the Milky Way is structured. So how do we know it's there? For a long time, the center of the galaxy was hidden from view by thick clouds of interstellar dust. In visible light, we could see only a bright, crowded region of stars in the constellation Sagittarius. But in the late 20th century, astronomers began to use infrared and radio telescopes, which can penetrate the dust. What they saw was remarkable. Stars near the center moving at incredible speeds, whipping around something invisible. One star in particular, named SS2, has been tracked for decades. It completes one orbit around the center every 16 years, sometimes coming as close as 120 astronomical units AU. For comparison, Pluto is about 39 AU from the Sun. The fact that a massive star can swing so close, moving at speeds over 5,000 kilometers per second, told astronomers that something immensely heavy but invisible had to be there. The only explanation that fits is a supermassive black hole. The size of Sagittarius, a star's event horizon, is about 25 million kilometers across. That sounds huge, but compared to its mass, it is actually very compact. 4 million suns crammed into a space no bigger than the orbit of Mercury is an extreme situation. The region just outside the event horizon is called the accretion zone, where gas and dust spiral in before crossing the boundary. As the material falls, it heats up to millions of degrees, producing radiation. This makes the area around a black hole glow, even though the hole itself remains dark. In 2022, the Event Horizon Telescope, EHT, produced the first direct image of Sagittarius A star. The EHT is not a single telescope, but a network of radio observatories across the world, all linked together to form a virtual Earth-sized telescope. By synchronizing their data, astronomers were able to capture the faint light around Sagittarius A star. The image showed a glowing donut-shaped ring with a dark center, the shadow of the event horizon. This was the first visual proof of the monster at the core of the Milky Way. Sagittarius A star is considered a quiet black hole. In other galaxies, supermassive black holes can be far more active, swallowing huge amounts of gas and producing quasars, brilliant beacons that outshine entire galaxies. A black hole is currently in a low-activity state, feeding only on small amounts of matter. However, evidence suggests that it has been more active in the past. X-ray echoes seen in gas clouds near the center indicate that hundreds of years ago, Sagittarius A star was flaring much more brightly. It may flare again in the future if new material falls into it. The environment around Sagittarius A star is extreme, close to the black hole. Stars orbit at breakneck speeds. Gas clouds are stretched and twisted by tidal forces. Occasionally, a star may wander too close and be torn apart in a process called tidal disruption. The remains form a stream of gas spiraling into the black hole, creating a temporary flare of radiation. Observing these events helps astronomers understand how black holes grow. The physics near a black hole is unlike anything we experience in everyday life. Gravity is so strong that time itself is affected. According to Einstein's theory of general relativity, time runs slower near a massive object. This effect, called gravitational time dilation, means that if you could watch a clock falling toward a black hole, you would see it tick more and more slowly as it approached the event horizon. To an outside observer, it would never actually cross the horizon, instead appearing to freeze at the edge. For the object itself, however, time would continue normally, and it would fall inward without noticing the difference. Inside the event horizon, all paths lead inward, nothing can escape, and the ultimate destination is the singularity at the center. A singularity is a point where density and gravity become infinite, and our current physics cannot describe what happens there. Some theories suggest quantum mechanics may prevent a true singularity, replacing it with some exotic state of matter or energy. Others speculate about wormholes or connections to other universes, but these ideas remain unproven. What we do know is that the singularity represents the edge of human understanding. Sagittarius A star also provides a laboratory for testing fundamental physics. The orbits of stars around it match the predictions of general relativity with high precision. In 2018, astronomers observed a phenomenon called gravitational redshift in star SUC-2, where light from the star stretched to longer wavelengths as it passed through the black hole's intense gravitational field. This was exactly what Einstein's equations predicted. Each new observation strengthens our confidence in relativity, but also pushes us to search for the limits of the theory. Another mystery is how supermassive black holes like Sagittarius A star formed in the first place. Did they begin as smaller black holes in the early universe, growing by swallowing stars and gas? Or did they form directly from the collapse of enormous clouds of matter in the first billion years after the Big Bang? We don't yet know. What is certain is that they play a central role in shaping galaxies. The relationship between black hole mass and galaxy properties, such as the speed of stars in the bulge, suggests that galaxies and their central black holes grow together. For life on Earth, Sagittarius A star is too far away to pose any danger. Its gravity, though immense, diminishes with distance. At 27,000 light-years, it has no direct effect on our solar system beyond being the central point of our orbit around the galaxy. But its existence shapes our understanding of the universe. It tells us that galaxies are not just collections of stars, but also hosts to invisible giants that govern their centers. Philosophically, Sagittarius A star represents both fear and wonder. On one hand, it is a reminder of forces beyond our control, a place where matter and light are trapped forever and where our laws of physics fail. On the other hand, it is a triumph of human curiosity that we can detect, measure, and even image something so distant and hidden. The fact that we can study the monster at the galaxy's center from our small planet is a profound achievement. As we finish our journey inward, we see how each step of the Milky Way revealed something different. The glowing band across the sky, the star nurseries of the spiral arms, the ancient globular clusters, the crowded stellar core, and finally this dark giant. The Milky Way is a layered structure of beauty and extremes, and Sagittarius A is its ultimate mystery. The monster at the center is not just a destructive force, it is also part of the balance of the galaxy. Without it, the structure of the Milky Way might be different. With it, we have a natural laboratory to study gravity, time, and the limits of physics. It has been there for billions of years, quietly shaping our galaxy, and it will remain for billions more. Long after Earth and the Sun are gone, Sagittarius A will still sit in the center, pulling in gas and stars, bending space-time, and marking the heart of the Milky Way. To us, it is both terrifying and inspiring. It shows us how small we are, yet how far our minds can reach. The Milky Way's monster is a symbol of both the universe's power and humanity's ability to seek understanding in the face of the unknown.